Anthony Raj. He has pursued his bachelor's, master's, and MPhil in physics. He then went on to pursue his PhD in physics at the University of Madras as well. He then went on to work as a lecturer at Tiruvalluvar Arts and Science College and Idya Engineering College for Women. Since the year 2006, he works as the lecturer and assistant professor at Loyola College, Chennai. With regard to research, he has published several papers in international journals, namely Radio Wave Propagation over Salem, Linear and Non-Linear Optical Properties of Pure and Doped Selenium Malate Single Crystals, and many more. He has also attended several conferences and seminars, namely International Conference on Materials Science and Technology, National Conference on Higher Education at Crossroads held at Loyola College, National Seminar on Crystal Growth 12 held at VIT University, and many more.
Welcome to E-Lecture series on BSc Electronics Practicals. In this lecture, we are going to see the LCR series resonance circuit. In this LCR series resonance circuit, we are going to calculate the resonance frequency of the circuit, bandwidth, quality factor, and inductance resistance. These are all the things we are going to calculate in this experiment. My order of the lecture will be as follows. Aim of this experiment, apparatus required to do this experiment, formula used to calculate the parameters involved in LCR series resonance circuit, then circuit diagram to connect the LCR series resonance circuit, observations made in the experiment, then calculations based on the observations and result. These are the things we are going to see in this lecture. Aim of this experiment: to study the frequency response of a series LCR circuit and determine its resonance frequency, impedance of a resonance, quality factor, and bandwidth. So, 4 parameters will be calculated in this experiment. Apparatus required to perform this experiment: resistance boxes, that is a variable resistance, then inductor, inductance coil, capacitance, capacitor box, then power supply, multimeter to measure the voltage across inductance, capacitance, and resistance, then function generator to give the input frequency. These are all the apparatus required to perform this experiment. To calculate the quality factor of this circuit, formula used is Q is equal to XL by R, where XL is the inductive reactance and R is the capacitance, which is equal to 2 pi F resonance into L, the whole divided by R. F resonance is the resonant frequency. So, to calculate the quality factor, we need to find the resonant frequency of this circuit first. Bandwidth of this circuit, that is, this circuit is responsive for what frequency range. That frequency range is called as bandwidth, or frequency difference between lower cutoff frequency and upper cutoff frequency. Here lower cutoff frequency says the value of the gain remains constant, that is lower cutoff frequency, or voltage across the inductor coil or resistance is constant. At what frequency the voltage becomes constant, then at what frequency the voltage starts decreasing. If you find the difference between these two frequencies, we can calculate the bandwidth of the circuit. This bandwidth depends on the value of inductance, capacitance, and resistance. If you want to be effective, if this circuit want to be effective for a frequency range of 10 megahertz to 20 megahertz, accordingly you have to fix the values for L, C, and R. This is called bandwidth of this LCR series resonance circuit. Then resonant frequency can be calculated by the formula F resonance is equal to 1 by 2 pi into square root of LC. That's LC is in the denominator. So this is how you can calculate the resonance frequency, quality factor and bandwidth of this LCR circuit. Next, some important theory behind this LCR circuit. An important property of this circuit is its ability to resonate at a particular frequency. That particular frequency is called as resonance frequency. This resonance occurs because the energy involved, electrical energy involved in this circuit is partly magnetic and partly electric. In inductance, magnetic energy is stored. In capacitor, electric energy is stored. When both the energies are discharged by the components, it will be oscillatory. So we get frequency from this LCR circuit. So resonance occurs because energy is magnetic field at inductor and energy transferred to one to the other within the circuit. This transfer of energy is oscillatory. The resonance frequency is the frequency at which the impedance of the circuit is at a minimum value. So to get resonance from a electrical circuit, impedance in that circuit should be minimum value. Equivalently, it can be defined as the frequency of the resonance at which the impedance is purely resistive. So that is also called as the resonant frequency. Impedance frequency at which the impedance is purely resistive is also called as resonance frequency. Then a key parameter concerning this LCR circuit is its bandwidth. The bandwidth is measured between, as I told earlier, the bandwidth is measured between the frequencies at which power passed through the circuit has fallen to half the value passed at resonance. That is called as bandwidth. There are two halves of the frequency, one above the resonant frequency and other below the resonance frequency. The difference between these two frequencies gives the bandwidth of the circuit. The quality factor is another important parameter in this LCR circuit. This quality factor is used to measure the characterization resonator of the circuit. This quality factor is defined as the peak energy stored in the circuit divided by the average energy dissipated in the circuit, average energy dissipated per radian at resonance. This is the definition of quality factor. So, low quality factor circuits are therefore damped circuit and lossy circuit, and high quality factors are underdamped and Q is related to bandwidth. Low Q circuits are wide band and high Q circuits are narrow band. So, according to our requirement, we can make the circuit as narrow band frequency circuit or wide band frequency circuit. All the bandwidths are depends on the values of inductance, capacitance and resistance. So, these are the three basic parameters of this LCR circuit: quality factor, bandwidth and resonant frequency. Now, let us come to the procedure to do this experiment. Before going into the procedure, just look at the diagram given here. Here you can see frequency source is connected to the capacitor, inductor and resistor. Here capacitor can have any value, inductance also can have any value, then resistance. All the three values decides the resonant frequency. Based on the resonance frequency, quality factor is determined. Based on the quality factor, bandwidth of the circuit is determined. Now, let us come to the procedure to do this experiment. First, keep the inductor and capacitor at constant values. Choose a particular value for the resistor. Measure the voltage across the resistor for different values of the input AC frequency. At the resonance condition, there will be maximum voltage across the resistor. That maximum voltage for which the frequency is called resonant frequency. Now tabulate the observations of frequency and the voltage across the resistor for different values of resistors. Next, plot the graph between the frequency and the output voltage. For what frequency the output voltage is maximum, that frequency is called as resonant frequency. Like this, you can calculate the resonance frequency from the observation. Then you can substitute this resonant frequency in the quality factor formula 2 pi f L by R. Then from that quality factor, you can find the bandwidth of the circuit. Then resonant frequency can also be calculated. So resonant frequency can be calculated as well as practically observed, practically measured from the graph between the input frequency and the voltage across the capacitor. This is the circuital arrangement for series LCR resonance circuit. This is the function generator. From this function generator, input frequency can be given to this series LCR circuit. Input of the function generator comes to the inductor coil. Here I have used 600 turn inductor coil. From the inductor coil, the capacitor box, condenser box is connected. From the condenser box, a resistor box is connected. Then from resistor box, the next end comes to the negative terminal of the function generator. Like this, inductor, capacitor and resistor are connected in series with the function generator. That's why it is called as series resonance circuit or LCR series resonance circuit. Now in this experiment, we are going to measure the voltage drop across the resistance for various input values. So first we are going to keep the inductor value and capacitor value constant and a particular value of resistance, how much voltage is dropped across the resistance for varying input frequency. We are going to measure that. In this function generator, the input voltage knob is kept at 10 volt. Then the frequency type of waveform to be given as input is chosen as sine wave. Using this function generator, you can get three types of waves. One is a sine wave, then a sawtooth wave and square wave. For this LCR circuit, I am going to use this sine wave. Next, the input frequency knob, frequency adjustment knob has got 5 options. 1 into the hertz, then 10 into the hertz, then 100 into the hertz, then 1 kilo ohm into hertz, then 10 kilohertz into hertz. Like that you can get a frequency of 1 hertz to 100 kilohertz can be obtained from this function generator. Input from this function generator comes to the inductor coil. Here this inductor coil inductance is fixed. This coil is fixed in 600 turn. Inductance of this coil is 9 millihenry. Then from there it goes to capacitor box. In this capacitor box, you can get a capacitance from 0.001 microfarad to 0.1 microfarad. Till that you can get variable capacitance from this capacitor. For this experiment, this capacitance value is fixed as 0.1 microfarad. Next, resistance box. This resistance box is also called as a decade resistance box. From this resistance box, you can get a resistance values from 1 ohm to 10,000 ohm, 10 kilo ohm. Till that you can get the resistance. To do this experiment, I have kept the capacitance value as 0.1 microfarad, then inductance value as 9 millihenry, resistance value as 1 kilo ohm. Now, I am going to keep the input frequency knob at 100 ohm. This variable thing is kept in 1. So, 100 into 1, 100 hertz is the frequency. Now, look at the voltage across the resistance. It is 0.75 volt. Here, we are using AC voltage. So, in the multimeter, the knob should be at 2 volt AC. We are not using any DC, 2 volt AC. So, for 100 ohm, the value, the voltage drop across the resistance is 0.75 ohm. Now, I am going to change this input frequency to 200 hertz. Now, I am going to keep the input frequency at 200 hertz. Now, see the voltage across the resistor. See the voltage at 0.73 volt. So, like that you can see a decreasing trend for various input frequencies. As the frequency increases, the voltage decreases across the resistor. So, this is the decreasing part of the frequency versus voltage knob. To get the increasing part, kept this to 10 hertz. As I increase the frequency, the voltage across the resistance increases. This is an increasing trend. So, in this experiment, we saw as the frequency increases, voltage increases. After a particular minimum frequency, further increase in the frequency keeps the voltage decreasing. That particular minimum frequency for which the voltage is maximum is called resonant frequency. For this circuit, this resonant frequency is 1 kilohertz. For this experiment, the resonant frequency is 1 kilohertz, inductance value is 9 millihenry, capacitance value is 0.1 microfarad, resistance value is 1 kilo ohm. Now, substituting all these things in the formula, Q is equal to 2 pi f L by R. Substituting all the things in the formula, 2 pi f L R will get the quality factor. Quality factor of the circuit will be very minimum. Then substituting that in the bandwidth will get a high bandwidth. So, it is a wider circuit to be operated. Resonant frequency is 1 kilohertz, bandwidth will be a wider one, then quality factor is very less. You can change the same circuit for different values and you can get the quality factor increasing. So, bandwidth will be decreasing. So, the same LCR circuit can be a wider bandwidth circuit and narrow bandwidth circuit, depending on the values of inductor, capacitor and resistor. Where is the application of this circuit? These circuits are applied in the receptor and variable receptor circuit or acceptor circuit. If we keep the values of inductance, capacitance and resistance as variable one, automatically varying one, or parameter dependent varying one, according to the incident frequency, values of the inductor, capacitor and resistor will vary. So, it will adjust its bandwidth, it will become a narrow bandwidth circuit or wider bandwidth circuit. This is how LCR circuit can be studied and various parameters can be calculated. Thus, in this experiment, we calculated the resonant frequency of the circuit. We got that as 1 kilohertz, and the bandwidth of the circuit, which is a wider one, quality factor of the circuit, whose value will be very less than the circuit is classified as wider bandwidth circuit. Thank you.